Hello and welcome back. Alright, so in the last video we started to re-implement our graph structure, or our graph class, so that we could have a more friendly implementation for working with graphs. Okay, so in this video we're going to go ahead and take a look at the completion of that type. Alright, so what we want to do is, the last thing we did is we defined this adjacency list. If we jump back over to our whiteboard, we can see that this is what our adjacency is. So we need to go ahead and write the code to create that. Okay. Alright, so in add edge, what we want to do is we want to create a new edge pointer. We're just going to call it E, create new edge, pass in source, pass in target, pass in weight. Sorry, there's no source. Pass in target and pass in weight. So this is why we created that handy dandy function or constructor up here. What we need to do is we need to go ahead and actually initialize our node and our target heights and our edge to what's being passed in. So there's two ways to do that. We can use the initializer syntax, or we can do it in the function body. I'm going to do the initializer syntax. Target T, weight W. Alright, so our edge is all fixed up and cleaned up now. Alright, so in our add edge function, we've created our new edge. So you'll notice that we're not going to do any error checking to see if an edge already exists. So if I come down here and create another edge between A and B and give it a different weight, we're not going to give the user an error that edge already exists. We could if we wanted to, but for now, I don't want to do that. We're just not going to do that for this portion of the video. Alright, so in our adjacency list, we now need to add that edge to our list. And I mentioned before that we have this indexing syntax, we can index it kind of like an array. Well, there's syntax that makes that pretty handy. We just use the array syntax, and then we just call the vector function pushback. And what that does is this source indexing gives you back the value data type over here, which is a vector of edge pointers. And so since we're just dealing with a vector, we can call pushback, and we pass in the edge pointer. That should actually be E. Then we pass in the edge pointer that we just created. Perfect. So there's one more thing we need to do in our add edge. So if you remember, our definition that we gave for the adjacency list was a list of every node in the graph and its relationships going out of that node. Well, as we have it implemented now, and we can see with the example over here, is that our adjacency list will actually be missing the D node. The key values in our adjacency list represent all of the nodes in our list. And when we go through here, the way that the map class works is whenever you call or index into the map, if the key value doesn't exist in the map, then it adds it to it. So in this case, we're going to get A added, we're going to get B added, we're going to get C added. And then this B call to it in here will just give us back that vector that we've already added an edge to B. For the B node it was to C. And then when we call A, it's just going to give us back that vector that has B, the edge for B in there. But D is never going to get added. So what we want to do is we want to always make sure that our target node is also getting added to our list. And because the way a map works, we can simply just do this. So what this does is it returns back the vector. We're just not doing anything with that vector. And so it's also going to make sure that the target node gets added to our adjacency list. I'll comment this out after we do print, and it'll be a little bit more clear on what's happening there. Okay, so now we have two more functions that we need to implement. There's the print, and then there's the graph destructor. Let's go ahead and do the graph destructor first. So if you look in our add edge, you can see that we're creating a new edge. So we're actually allocating new memory on the heap. So that means when our graph class goes away, currently we're going to have memory leaks for every edge that exists, or that the user has created or added into our list. Sorry, into our graph. So what we want to do is we want to iterate over all of the adjacency node, or all of the nodes in the adjacency list, delete all of the edges from their associations, and get rid of that memory. Okay. So in order to do that, we need to create an iterator that goes over our map. And so maps actually have a built-in iterator just like vectors. So let's go ahead and write that. So we can use our edge map, and then iterator, call it IT, and that's going to equal adjacency list dot begin. And then while at does not equal adjacency list dot end, increment the iterator. All right. So now you remember that I needed to iterate over all of the edges and delete those. So we need another internal loop here to iterate over the value of our map. Now, the implementation of map in C++ STL library, there's two parameters. There's first and there's second. The first corresponds to this left side, this key value. The second field that references the value side. Okay, so we're going to need a new standard vector edge pointer iterator. Okay, and we're going to call that EIT, which is for edge iterator, and that's going to equal our iterator second. So this dereferences the iterator, points to our vector array, or sorry, points to our key value pair that we're getting back. Second gives us this reference into the edge pointer vector, and so we can just call the begin function on that vector to get the beginning of that iterator. And so while the iterator does not equal it second dot end, EIT add. And we just barely made it on the screen with that. Oops. Extra space there I don't need. Fit it a little bit better. Okay. And so if you remember, iterators are pointer to our items. We need to dereference our pointer to get to our edge pointer to delete that memory. So we just do delete star EIT. And so this follows the iterator pointer into our edge pointer, and then we can delete the memory at the address that the edge pointer is pointing to. Perfect. Okay, so that's going to go ahead and clean up our graph so we don't have any memory leaks. So let's go ahead and implement our print function now. All right, so our print function is a constant function, so we're going to actually have to use iterators a little bit different. By default, an iterator allows you to modify data within the data structures, but we're going to need to use a constant iterator. If we don't use that constant iterator, we'll get compile errors about type mismatching. And I'll show you what that error looks like. So for our print, what we want to do is, if we jump back to the whiteboard, what we want to do is we actually want to just, this is what we're going to print out. The same thing that I have written here. Okay. So in order to do that, we need to iterate over our map, and then we need to iterate over our edges, which is a lot like what we did in our destructor. So I'm just going to go ahead and copy and paste that code down and modify it a little bit. So like I said, we're going to need to use constant iterators. So what we use is, it's called const underscore iterator, and that gives us our map. If, let's say I compiled here, and I'll show you what that error looks like. It says build fail. It says, oh, conversion from normal iterator, blah, 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 to non-scalar type, constant pointer stuff in there. Basically a big long cryptic error message that says, hey, you need to use a constant iterator. And then that's the only change that we're making to those loops. And then so we're going to, well, to the actual declaration of the for statement piece. Go ahead and delete the line that says delete star EIT. So above this, I want to actually print out our node name. And so I'm going to do that and surround that name by bracket or with brackets. Our map first. Remember, our first points to this leftmost key value in our map, okay, which is going to be our node, which are just being represented as characters. And then I'm going to do a square bracket and this little arrow. And then in here, in our inner for loop, we'll go ahead and print out all of our edges and the weights associated with that edge. Okay, so we do standard cout. We're going to need to put in parentheses, dereference the edge iterator. Then we're going to have to use the arrow syntax to dereference the edge pointer that we're getting back from our edge iterator so that we can pull out our target node. Okay, and then we're going to put the edge cost in parentheses. We're going to do the same thing. Oops. Weight. And put a comma space at the end of it. Okay, so just to be clear again, we dereference our edge iterator. That gives us back an edge pointer. That's why we need to use the arrow syntax so that we can dereference that edge pointer to get the weight field off of the edge. Okay, and so at the end of this, we actually just want to create a nice little output line here. All right, so we have our print function. Let's go ahead and build. And we see all of our compile errors are non-existent. And if we go ahead and open up the debugger output window and we run our program, we can see that, hey, this looks a lot like what we drew on our whiteboard. We have our node A. It has a relationship to B that cost us 1. It also has a connection to D that costs us 10. The node B has a relationship to C that costs us 2. D is 6. And if we look down on our code, we can see, hey, you know what? These are actually the same values that I passed in. Great. And then we see D. Hey, D has no outgoing relationships. Now, of course, we could, since we're doing a non-directional graph, we could actually add the lists backwards. And so that you could always see the relationships. Let me go ahead and actually do that for you, and you can see what I'm talking about here. So in our add edge function, right here, we say source pushback e. Well, we would need to create a new edge, so that target. That way, we'd have to actually put a target on there as well. So we could just do that. Do pushback new edge, and this is actually going to be source. Weight. If we build it, put the right number of parentheses, open over here and run it, and then you can say, hey, you know what? We actually have the opposite associations as well. So A goes to B goes to D, perfect. B goes to A goes to C goes to D, perfect. B and D, perfect. And D goes C to B to A, and those values are there, and all is happy. So that is our video. Oh, what I wanted to show you is if we didn't do this, okay, let's comment this line out and just put back what we had, which was adjacency list target. Well, if we didn't, so if we build this, go back over here, run it. This is what our original example looked like. Now, if we didn't have this piece of our code right here, and we build it, we jump over to our debugger output, you'll see that we're always going to be missing this D node. So that's solved by either doing this call or by doing this to add the opposite edge. Now, if we're doing a directed graph, that is a graph that has a direction associated with it, which is basically what we implemented the first time. You're always going to be missing the graphs. So, you're always going to be missing a node from the graph. So if we're doing a directed graph, essentially you use this line of code. If we're using a non-directed graph, you basically use this line of code. And so we'll go ahead and leave this non-directed graph implementation in here. And yeah, and that's that. So for the next video, we're actually going to go ahead and talk about how we can find the shortest path to, or from one node to another node. All right, thanks.